Hello, everyone. My name is Paul DeBar. I'm a distinguished visiting fellow here at the Center for Global Energy Policy at Columbia University. Today, we're going to discuss the future of fusion as part of a first of a multi-part series on energy technology revolution. Let me quickly say this event is being webcast live with full video being available online in the coming days. For those of you joining us by Zoom, you can submit a question for the panelists at any time by clicking on the Q&A button at the bottom of your screen. We're here today to talk about the recent jumps in the prospects for fusion power. This advent has led to significant new U.S. policy and funding increases over the last 5 years. But much of the clean energy policy community has little exposure to the current state of play of fusion. Many say that we need to focus resources on new energy types that can make a difference by 2050. Most of the energy policy community are not aware of the recent advances in fusion and are not aware that it is increasingly likely that fusion can be a significant contributor to energy production or earlier than that date. Today, we're here to discuss with the energy policy community that the fusion technology prospects have made great strides, and that the view of fusion it being continuously 30 years out from being reality is no longer the state of play for technology. And given the advantage of fusion has having all the positives of current energy technologies and none of the disadvantages, the energy policy community should make room for this possibility and appropriately support this potentially massive revolution. I'd like to introduce the two panelists here today that we have. First is Sir Stephen Cowley. He is a theoretical physicist of global renown and international expert in fusion energy. He's a former president of Corpus Christi College, Oxford, and he was CEO of the UK Atomic Energy Authority and head of the Column Fusion Center for the UK outside of Oxford. And he was knighted by the Queen in 2018. He received his PhD in astrophysical sciences from Princeton, and he returned to Princeton a few years ago to lead the Princeton Plasma Lab, the lead Department of Energy Fusion lab. When I went back to his previous lab in the UK, I asked his old colleagues if they are addressing him as Sir Stephen, and they were non-committal on that formality with Steve. And finally, Steve is a master of TED Talks. As he has previously said, he likes it when Mr. Putin turns off gas supplies to Europe since his budget goes up as a result. How's that working today for you, Steve? Quite convenient at this time of budget negotiations. And then the second panelist we have here today is Dr. Bob Mumgard. Bob is CEO of Commonwealth Fusion Systems of Cambridge, Mass. Bob is co-founder at CFS, one of the leading private fusion companies in the world. Bob has a great story of taking a challenge that was funding at MIT at the time, not so long ago, and pivot to accelerating hopeful hitting the major fusion milestone of a net out containment in the next few years. Everyone should read the recent New Yorker article about that history of Bob and his co-founders. And Bob has been quite engaged over the last 5 years on ideas for fusion energy policy for the country. Many of the talks and interviews that Steve and Bob have done have focused on the physics and the technology of fusion cores, as well as Bob making analogies to Homer Simpson, Jelly of Donuts, Keanu Reeves movies, and discussing grad school heliophysics. We couldn't get two better panelists representing the leadership of national labs, academia, and the private sector for fusion, which has grown in interest over the last few years. I would like to start off the panel by giving an opportunity to Steve and then Bob to give some introductions on the state of play of the fusion community.
Thank you very much, Paul. It's a great pleasure to be with you today. This is a very interesting time for fusion because we're beginning to see the end game. Fusion has been around really since around about 1950 as a potential energy source. And there's always a joke, right? It's 30 years away and it always will be 30 years away. But actually, there's a consensus in the fusion community that that is no longer the sort of timescale we're talking about. Nobody can be absolutely firm about timescales, but the National Academy of Sciences had a panel of experts from the nuclear industry, from the energy industries, from fusion science, fusion engineering, that reported last year that put a timescale on actually producing some electricity from fusion. That panel was looking at producing the first electricity from fusion sometime in the late 2030s. This is the end game. And being able to come to market with something that actually is in the price range for the consumer and deliver a firm energy source, one that can live alongside renewables in a integrated energy system on that timescale, I think would be game-changing and incredibly important for the goals of this administration and the previous administrations to decarbonize our energy supply. It couldn't happen fast enough, if the truth be told. Thank you.
All right. Thank you, Steve. And Bob, some introductory thoughts from you on the state of play of the fusion community?
Yeah, I think Steve said it well about you can see the end here, and I think that it's really important to also realize that we're starting to see different paths to get there. That it's not only one path, and it's not a forever path. And in that way, it looks a lot like how other technologies have come to market. And in fact, I'm reminded of before CFS was CFS, MIT was asking a question of, how does fusion evolve? Not just technically, but how does it evolve as an ecosystem of people and institutions? What should we expect to see? It was really an introspective question on even whether MIT should be involved in fusion anymore. This was about 6-7 years ago, and that's where I was involved. I'm in addition to fusion and plasma physics, I have a soft spot in my heart for the history of technology. And when we looked across the whole ecosystem of why were there investors putting money in private fusion companies, that was a relatively new thing at that time. What were the roadmaps that different countries had? What were the different tools that were in the policy discussions at the time around other new emerging technologies? And we came to the conclusion that fusion was likely to travel a path that was a well-worn path. Of how you go from a purely scientific endeavor, which is builds the foundations and builds the knowledge and the tool sets, to something that straddles between academia and private industry, that factors in the needs of the customer, the pull on the technology, in this case, greatly accentuated by climate change, to something that is a ongoing enterprise that actually is out in a market and being built and delivered at scale, supported by continued reinvestment and increasing investments in academia and the areas that are around in industry, really. And so we could chart that out. And about 5 years ago, we actually did that exercise. We charted that out, and you could see that the pieces were all at the table. And now I think that those pieces are starting to get into the right positions, even. Both in the United States and the UK and the European Union and China and other places. And so it's a very exciting time because it's dynamic. It's got different players, different new institutions, new companies. It's got different classes of new investors. It's same time though, it's got a long history of technology and people have dedicated their entire lives to this. And so I think we're privileged to be at that moment, and we're also I don't want to say it's a coincidence. I think there's a lot of causality in this as well. But this is happening at the moment. The world's looking at how are we going to meet the commitments that we have to meet to have a livable planet. And so the questions really are, what's the way forward? How do we balance the different needs on the science, technology, ecosystems, and policy to try to find a path forward that gives the best probability of success for the ultimate end goal, which I think everyone is increasingly well aligned on.
Okay, thank you, Bob. So first question I want to ask, maybe Bob, I'll ask you to maybe answer it first, and then Steve. Given the state of play in particular, Bob, of paper you just company just published, which is really the map to a 10 times out fusion core that your really groundbreaking announcement here in August or September, I've lost track of time here, on your magnet that really sets up that. Could you comment a little bit on what's the state of play of the prospects from a timing point of view, and the steps to get from where we are today to, let's say, a first demonstration plant that's actually making electricity, the very first one, a little bit, like Fort St. Vrain or others that happened back in the old days for fission.
Yeah, so I think if you break it down into different steps, and I think the national academies and other roadmaps around the world have done a good job at breaking this down into steps. Where we're at is we can now see that the ability to create a plasma that can make more power out than in, many times more power out than in from fusion, that is something that we're having increasing confidence in the world's ability to do. That confidence is embedded and embodied in the ITER project, which plans to do that and reach that milestone in about the 2035 timeframe with a large tokamak. It's also in the simulations and tools that we use to support that project, and we're continuing to validate as experiments worldwide. And CFS's point of view, I'll come back to that. So there's the first step of this: can you build a physical system that actually does the heart of the whole thing, of making more power than in the plasma system? Once you have that, you've gotten across something that we've tried to do for a very long time. It's necessary. It's not sufficient. We still have to figure out how to turn that into a practical system. So how to put materials around there that can be maintainable and can be the right lifetimes, how to build that in an economical system, how to do some of these fusion-specific auxiliary things of closing the fuel cycle, and some of the non-fusion specific things that need to be coupled to fusion, like balance of plant, of turning the heat to electricity, those types of things that are really plant integration steps. And so usually what you see in roadmaps is you see, a net energy step and then a power demonstration step of fusion electricity on the grid. The timeline for that is something that I think is an interesting question to ask, as different entities try to do different things. So ITER has one timeline, which puts the electricity demonstration step in a follow-on machine in the later half of the century. CFS, we think that the path here can be made into a much smaller set of machines, machines that have been studied widely by the U.S. and particularly the United States, and compact high-field tokamaks, places like Princeton previously, with coupled to a new technology in the high-field magnets that we've now developed out of new materials. And so that through new materials and through new ways of operating, we could shorten both of those steps. We still don't think that it makes sense to do it all in one step. And when you look at that sort of timeline, it means that maybe we have, in the late half of the 2020s, we have a net energy fusion machine somewhere in the world. At CFS, our goal is to deliver one just about an hour west of Boston. And then that would put the opportunity in the 30s to have an electricity producing machine. And that timeline is maybe slightly more aggressive than the National Academies recommend for the United States, but similar to the timeline that the UK is trying to execute in their government program. But it's a much faster timeline than I think the world appreciates broadly.
Steve? You're still on mute.
You would have thought by all of this time Zooming, we got this right. I think some very interesting things happening, and I think I agree in rough generality with what Bob has said. But there's some very interesting things happening in some of the experiments around the world. The Germans have pushed forward a concept called the Stellarator. And the Stellarator was the original concept that the Princeton lab was founded on. And it's a machine that doesn't carry a current in it. All the current is in the external coils that shape the plasma and make it happen. Now, when Spitzer proposed this in the 50s, it was just impossible to build. because it requires a precision, and it requires a precision of calculation that requires today's supercomputers to be able to really simulate properly and optimize. But it has the advantage that it's steady state. And it has the advantage that it doesn't have some of the instabilities that the other machines have. And it's coming up like a steam train at the moment. And they're getting performance like all the other, like the best machines in the world out of that device. And they had optimized it on 1990s computers. And we're trying to now push this forward using sort of the power of the US's big computers, to be able to optimize a configuration that will make a really attractive energy system out of that. And there's just so many different configurations that you could do, so it's perfect for the way science is going at the moment. Big data, big calculations, big optimization. I think this might be actually a shortcut to fusion. And so one of the things that it's just like the sort of the beginning of flight. Many technologies are sort of starting to get close. And Bob and I would probably not agree on which one's going to get there first, but I think we can all agree that actually all the technologies are sort of knocking on the door of the performance levels that we'll need for an actual reactor.
So in the last 5 years, there's been a lot of policy changes, increased funding, different programs that have happened in the U.S. In retrospect, kind of looking back on what's happened, studies, academy studies, and so on, which ones do you think have had which policy kind of changes in the community have made the biggest impact on advancing fusion, it kind of as we kind of look back in time and things that were done?
I'll have to take that one. So, we're almost entirely privately funded as a company, and so it's actually an interesting thing where we look across the whole international landscape and think about where to put our resources, where to put our people to take advantage of opportunities. And in the U.S., there's a lot of discussion around policy, and there's a lot of policy, but it's not actually being implemented. And so we're still at the sort of the early stages of somewhat looking around and figuring out what it is the U.S. is going to do. Whether that's implementing programs to partner with the private industry and ways to build demonstration machines, or whether that's new facilities to build test stands for some of the technologies that are going to be fusion specific that all the different confinement concepts are going to need, or whether that's even just building new confinement starts and experiments. The U.S. hasn't really done much. In many ways, the lead is, if you look across the new starts, the lead has moved significantly towards the UK, who's made large investments in Cullum and other places. But I think the US has laid good groundwork for what needs to be done, and has the scientific and the roadmaps and the plans for what to do, and has built a constituency and policy and government to actually follow that through with appropriations and actual construction of new things as we transition from the tool sets that have gotten us as far as we have gotten into the tool sets we're going to need for this next era. And so it's sort of been waiting year by year to see what exactly is going to get implemented on the ground in shovels. And I think we're waiting for that.
Steve?
I think it's a mixture of policy and a growing awareness from an investor community that this might be something that is really worth investment and really worth developing. I think a lot of the investors in fusion are there for two reasons, not just to try and make money, but actually to do something really worthwhile with their money. And I think that's very important because it's a high risk situation. But marrying that to some of the policies that started coming in the last administration and have been continuing in this administration, which is to do public-private partnerships, to start to put together the public programs and the private programs and saying together we can do something really much faster, perhaps take more risk, and develop fusion with more net capital going into it. Do you think the energy the energy market in the world is, I don't know, 8-10 trillion, something like that, right? And if fusion were to be 40% of that market, 30% of that market in the future, right? It's a heck of a business. And I think people are starting to think that, and starting to think, if we're really getting close to the end of the scientific development and more towards how to make it work in an engineering sense, then maybe it's time that money starts flowing from the private sector. And I think, Bob's company, companies like TAE, which is a company out in California looking at proton boron fusion. We have some very interesting ideas in those kind of areas. There's an excitement around at the moment about this.
So heading down the road, Bob, which you kind of started on your answer there, which was the retrospective, kind of question. On a prospective point, Bob, as you mentioned, there's been a lot of mapping out of different ideas by the national academies and advisory board at the Fusion Advisory Board at the Department of Energy. So there's a few inputs as you summarize there. Obviously, there's a lot of input from a lot of different reports. But from your opinion, what specific policies that might have been mapped out in those, or maybe elsewhere? If you were, there's a lot of people on this Zoom are from the policy area. So what would you say to them about what specific policies to drive towards? Once again, the goal is nothing against heliophysics. I love it personally, but if we were trying to target an operating fusion power plant that's cost effective, what sort of policies do you think would have the biggest impact to try to accomplish that goal?
Yeah, I think we can look historically at this, and I think the policies that recognize that the private sector and the academic lab sector are different, and that's great. That they are different and they have different strengths and they have different weaknesses, and that together they can actually function as a system that can advance things very quickly and create different types of value for different constituencies. And I think the clearest example in my mind and many of the people I talk to's mind is the relationship between NASA and the private space sector. That we went from a system that was really dominated by government laboratory equivalents and contractors to deliver low Earth orbit. And de-risked a lot of the technologies to do there. Not all of them that are needed to make it economic, or all of them that are needed to make it a bigger and bigger market, such as the reusability and advanced manufacturing and stuff like that. But they de-risked the basic concepts. And what NASA worked with to really supercharge the orbital sciences and SpaceX companies in they called it the COTS, Commercial Orbital Transport Services Program. It was really a novel public-private partnership where the risks that the companies could take were different than the risks that the public program could take. And the companies were much more attuned to what the market needed. And between working together on that, plus the technology that's been developed in the labs, they could get to new systems that could be competitive in the launch market. And of course, that led to SpaceX's dominance in the launch market today, and also led NASA to be able to leverage what SpaceX can deliver and think about the next thing that needs to be done in space exploration, and develop the next generation of tools, next generation of missions. And that's been, I think, a very fruitful partnership. And it's also something that, the money that was spent in that partnership, you can actually look at the tax receipts from SpaceX and see that the government's been paid back many times over through the success of that program. And so thinking through those types of policies that are sort of outside the box of just pure science policy, but also aren't just pure applied energy policy, but where there's at the intersection, those are very interesting. And in the recent bill that was passed the end of last year, actually enabled they authorized a policy for the U.S. to try that in fusion, and additionally, the U.S. has actually started that in fission. And so, we're seeing those types of models get tried in different sectors. And we think that fusion is a sector that this could be very interesting in.
So I think I just heard Bob say that we should fund what has been authorized on the similar program. Congress has already authorized that program, and I think I heard Bob advocate to get that funded to basically take that NASA model and apply it to fusion.
And just, as a one added note, I think you hit it right about, what's been authorized, because also in that same authorization is some really important test stands and some really important programs that set up that next generation of technologies that are also things that, the government makes investments that everyone can use, and including in government researchers, but also private companies and others. And those are also, the equivalent of building test stands for NASA, for instance, is basically.
All right, Steve, what do you think?
Well, I have to say that
the forward-looking policies that you think would make the biggest impact?
well, definitely what came out in the House authorization is a very progressive program that would take us forward much faster than we're currently going. It includes a public-private partnership program that Bob has talked about. It includes things to start to look at some of the other ideas that are coming up in terms of, we tend to call them alternate concepts. But I am a believer that we don't have every single idea yet that's out there. We may be able to produce some electricity, but there'll be an evolution of this technology through time. And I think one of the things that's really changing the field, I'm going to go back to a point I made before, which is, and this is also in part of the authorization, and that is, we're now able to calculate roughly how these things, not just roughly, quite precisely really, how these things work. And that means, instead of just building 110 of them and figuring out and selecting the one in a sort of Thomas Edisonian approach, where you build 50 and you pick the best one, we're able to do a lot of the work based on the science that's been developed in the government programs over 60 years. And that sort of use of computation is something that we couldn't have done even 25 years ago. And this is making a huge difference. And if you look at what's in the authorization, at this point, there's also the beginnings of a suggestion that we need to really fund a center for the computation here. And I think that this would help the private companies, because I think private companies can't afford all of the deep bench of science that are in the national labs. And it's our job to sort of stand alongside the private companies and help them understand their concepts and optimize their approach forward.
Yeah, I would make a comment. I got a phone call from someone over in Europe who was thinking about, not from the UK, but from elsewhere, who talked about moving to the US because of availability of various different aspects, the sort of things that both of you are talking about. Let me ask you about, Bob, you just brought this up, and Steve, you're actually the architect of this, so you're two great people to ask this. Let's talk about competition globally from a policy point of view. From trying to target, as both of you commented, to try to get to a not only a NetApp core but to an operating power plant. Clearly, the UK has invested historically, Steve, under your leadership, in creating a hub around your old lab. But they haven't stopped after you left. They picked up your baton and kept running with it, including recent expansions for that support, and including recently around trying to set a regulation strategy, the most recent aspect. Can both of you comment about what you're seeing in the UK or elsewhere? The UK seems to be the most obvious about what they're doing. Bob, as you kind of made references to, what do you see them doing, and what can the U.S. learn from a policy and an investment point of view to continue to advance the prospects of NetApp fusion here in the U.S.?
I'll turn it to Steve first.
Steve, as a person who organized it all in the UK.
You're giving me far too much credit. Look, it's one of the things. It's been a very interesting year in energy in the UK. right? UK is heavily investing in wind, and offshore wind is very good in the UK. There's that great big ocean next to us, and the wind blows reasonably steadily, but sometimes it doesn't, right? And they've had a couple of low wind months in this last year that have really been shockingly low. And you're starting to have an energy system that's really leaning on renewables in a way that we're all happy that it does. But the importance of firm energy sources, sources that can be turned on and turned off, and that don't rely on, the intermittency of renewables, is really understood, I think, in the UK at the moment. And it's one of the reasons that the UK has supported an expansion of conventional nuclear power stations. But there's also an understanding that fusion would make a great replacement for conventional nuclear, and to move that forward. And so the STEP program in the UK, which my successor at UK Atomic Energy Authority has really pushed, and he's an incredible executive, has really energized both the UK government and the Prime Minister himself into saying, we've got to push fusion forward. But there's one other player in this game you didn't mention, Paul, and that is that, China's watching very, very carefully. China has been training masses of graduate students and engineers and people in fusion technologies. They're in ITER, but when you talk to the Chinese fusion program, they say, why are you in ITER? Well, you see, you learn things from building ITER as well as learning things from operating ITER. And they're learning from building ITER, and they want to start to move. Their plan is to accelerate almost simultaneously with ITER to electricity. And so they're learning, they're moving, and they're investing at levels that are just eye-watering. Their energy system is going to be very different than ours. And one of the difficulties, I think, for anybody entering the American energy system is how competitive it is, how difficult it is to put new technologies into it, and how relatively easier it is when you have a nice authoritarian government to back you up. So it's a very interesting situation in the world at the moment.
So I'd like to ask a question about the comparable of the development of fission power plants in the 50s. And Steve, you had some interesting thoughts when we've talked about in the past about how Rickover looked at developing the first fission reactors and what was learned, what was done in taking that new technology with somewhat similar challenges, around neutrons and thermal flux and all the, a lot of the same topics, different numbers associated with them, but similar topics. And what maybe was learned there, and what could we learn from that today in terms of how to for people like Bob here to drive towards something that's applied and on the grid.
I wish I was as smart about what Rickover did as he was. I mean, it's remarkable that they managed to fit, a nuclear power plant inside a submarine in such a short number of years, and make it work. It's been a marvelous technology for submarines, but in that development, it wasn't that they tried one thing. They tried lots of things. And this is one of the things that limited resources in fusion have driven us to. We're tending to just try one thing. And if that doesn't work, then we try another thing. If you want to get things quickly, you've got to try several things at once. And I think that program did that. They were also very pragmatic. They didn't have to solve every problem at once. And get going. And I think Bob will speak to this, I'm sure, CFS, not trying to solve every problem with their first device, right? You make progress by building things. You don't make progress by just thinking. You have to build something.
Yeah, I'd follow that up. Like, I think one of the best compliments I've ever gotten was someone that said, this sounds like something Rickover would do when they looked at the plan, which, to Steve's point is like, the trying things, but also not being afraid to sort of bull rush ahead. Rickover was able to really energize the industrial base to go build things, transfer it out of the academic environment and into the shipyards. And the reason that the world is powered by light water reactors today is because you needed to be able to make pipes. And shipyards are good at pipes, and shipyards built submarines. And Rickover was able to draw those connections together, which means that you didn't have to have the perfect solution to start. You had to have a reasonable next step forward and a reasonably clear path, or a few paths and a strategy to navigate it. And I think that's, to the global competitiveness part, that's what the U.S. is actually uniquely good at. Like, we don't need to have a centralized plan way to develop fusion energy, but we need to have a centralized sort of strategic view of where we want to go and of what gaps need to be filled and who's going to fill them. And I think that the UK is somewhere in between us and say China in that, where they have a bit more of a centralized view, but at the same time are trying a couple different things to move forward and are leveraging existing big heavy industry. And in the US, I think we have a long history of the science and the computing and the sort of understanding of the fusion systems that is much better than many places in the world. And then coupled with the sort of risk appetite that startups can bring, of like not being afraid to fail, try something, break it, try again, break it, plus the portfolio of companies and approaches that the U.S. has accumulated that could lead to different attributes in the fusion systems that could be seen by different market players as more advantageous or less advantageous. I think that whole sort of somewhat chaotic ecosystem is a really a big advantage to the U.S. entrepreneurial, just this public-private landscape. And I we're starting to see that emerge in fusion. And I think some of the policy changes that people are talking about and some of the mindset changes that have happened recently, and people that maybe were dismissive of fusion before, I think that's all tailwinds.
Maybe if I can summarize. Oh, sorry. Go ahead, Steve.
Well, one of the big debates, which I thought was very interesting, that the National Academy panel that reported last year had, was what would you want to do with your first of a kind? How much would you want to prove? Would you want to prove simply that you can just do fusion? Actually, we've done some fusion, so you want to do more than that. But or just produce a little electricity? Or do you want to prove that you've solved all the problems that fusion needs to solve to be, a real competitor in the energy market? And this is a very difficult thing. You don't want to prove that fusion won't work because it's too expensive, because you haven't looked for the ways to make it cheaper. But you also don't want to go so far down the road that you never actually do anything at all. And that's one of the dangers of overlooking. Back in 2009, when I was running the Atomic Energy Authority, we in the European Fusion Program had a committee of utility people who came together to talk about, okay, what should we be aiming for our first of a kind? And they said, that's pretty simple. Just a megawatt or two, right? Just produce some electricity. Once you've done that, then the belief and the ability to move forward, that will unleash the kind of funding that you've never seen before. Because everybody recognizes that fusion is really a wonderful way to make electricity, but not everybody believes that it will happen. Once you've shown that it can happen, that will unleash the huge power of capital that will push through the remaining problems to the end. And this is a very interesting time, because we're having to make that decision. How capable should a pilot plant be?
If I can maybe just kind of condense what you both said and put it in kind of traditional current venture capital words, the fast failure strategy of what Rickover did before he knew the term fast fail, building things that make important but incremental steps, proving it out, and showing progress. I think is what I heard both of you say. For the people who are on the phone who are not part of the Fusion Advisory Board community at the Department of Energy, there was quite a bit of questions on the exact points that Bob and Steve were just mentioning about 4 years ago, when the U.S. government decided to increase a lot of funding, but they were very adamant to Congress that progress needed to be made and needed to be seen. And I think that certainly happened. Shifting to something, Bob, you were talking about, which is supply chain, both material but also people. I get a lot of questions about both of that. It's a little dated, but I remember, Bob, you talking about HTS supply chain and fabrication when you were just beginning to talk about if you were successful about that chain and that availability. You've come a long way since I've heard you talk about that initially, but maybe if both of you could comment to both the physical supply chain and the people supply chain issues, availability for what you think needs to be done as this ramps up. Bob, why don't you start?
Yeah, we oftentimes talk about the technology, right? But the technology is people building things, right? If you break it down to that, it's like, where are you going to get the people, and where are you going to get the things? And I think Fusion has a fairly unique thing in the energy landscape, which is that it can reuse a lot of the people and things that other energy technologies use, right? It's a thermal source, so it can reuse a lot of what's out there, even installed today, but also the manufacturing. Most of these machines are large, high precision manufactured things made out of metal and all in the right shapes. There's not any magic dust in a lot of them. There's a few Fusion specific things that we had to get right, and we got to be able to make more of, and there's a few things that we have to adapt to Fusion uses that we have to convince the existing manufacturers to do it a little bit differently. And I think one of the things that I'm seeing as out there, letting contracts for Fusion components for our next machine is that the manufacturers are very excited to be involved in that. They see that Fusion is coming. They see that it's going to be a potentially big market, and they want to gain advantage in there. And so they're eager to try new things, whether that's new ways to build lower cost refrigerators, or whether that's new types of power supplies, or whether that's getting experience in building the types of steel that's needed for magnets, or whether that's building entirely new supply chains for, say, the superconductor that we use. So that's very exciting. And then at the same time, the people side. So the first and foremost, we're going to need more people that know about Fusion. And one way to get them is to continue to grow the academic world. When Boeing was able to first, commercialize airplanes, we didn't see a drop off in aerodynamics people studying that in universities. We saw an increase, right? And same with Rickover and Fission. And so, being in a position to be able to increase the supply chain of knowledgeable people in Fusion, China's invested in that a lot. And where is the U.S.? What does it take for a dean to add a new Fusion faculty? We know that's also not going to be enough. It's not just PhDs, and as much as I have a PhD, I like PhDs. It's not just them. You're going to need masters and technicians and bachelors. You're going to need a whole workforce to be able to do this, and we have to pull that workforce partly from areas that they've been trained before. Adjacent industries, which Fusion pulls from electrical engineering and mechanical engineering, sort of the STEM, and increasingly computation and design. We have to be able to pull from them and teach them about Fusion quickly and get them into the flow. And really the private Fusion companies are now at a scale where our consumption of that sort of talent into the companies is actually starting to hit some limits. There's maybe approaching 1,000 people in the United States working in private Fusion companies, or very closely with them. And so we're gonna have to start increasing those if you want to make a difference in any of the actual energy on the grid. And the time scale of replicating expertise is quite long.
Steve?
It's very interesting, that there's an upswing again in all of the graduate programs doing fusion. I know MIT's had a huge upswing in the number of applications we have at Princeton too. People are very interested in this. There's a growing realization that decarbonizing our energy supply is a almost existential challenge for the planet, and people want to be involved in that. And so I'm very optimistic that we will have, a large number of well-educated people to bring fusion to market on that time. I think there's some very interesting things, though, of course, with the development of new materials, your high temperature superconductors, Bob, being able to produce those cheaply and in large quantities is going to be very important. I've got very interested technically in the use of permanent magnets to make the shaping fields of stellarators, and I'm personally interested in low field devices, and permanent magnets make a very good choice in there. But we have to have neodymium, and neodymium price just shot up this last year. It's not that probably we can't find plenty of neodymium, but we have to do it. And there are a number of challenges, I think, and the National Lab System is kind of rising to those challenges. If you could invent a permanent magnet that made 2 or 3 Tesla fields easily, and there are some very interesting sort of suggestions of that in the scientific literature right now, it would really help fusion.
Okay, great. Well, I'd like to shift to our Q&A portion here. Again, for those of you watching online, my name is Paul DeBar. I'm here with Sir Stephen Cowley, Director of Princeton Plasma Physics Lab, and Dr. Bob Mumgard, CEO of Commonwealth Fusion Systems. We're discussing nuclear fusion. We will now open it up to questions from the audience. For those of you joining by Zoom, you can submit questions for the panelists at any time by clicking on the Q&A button at the bottom of your screen. I'll go ahead and start with capital raising. A question here about venture capital. Right in line, I think Bob is as good as it gets in the world on asking this question. So, could you comment to the availability of the change in private capital availability to execute on some of these things that you've been discussing here today?
Yeah, I'd actually put it into two eras. There's sort of the pre-pandemic era, and there's the post-pandemic era. And I don't know if the pandemic had anything to do with it, but it certainly is a good delineator. Previously the venture capital models, were all based on software. And so that's not a great fit actually for doing things where you're not moving bits, but you're moving atoms. It has timelines, it has risk profiles return profiles that don't really match, say, building fusion companies. So fusion companies in general, I would say had a tough slog in raising private money. Able to do it, but you really had to be selective and had to be strategic on where you spend your time to do it, because you could just wear yourself out. But I think what's happened in the last year is people have opened the aperture to other models. And they've gone back and said, well, venture capital started out funding silicon and hardware. And that looks like we could use those models. And then have also looked and said, the next platform, the next thing that is as big as compute or as the internet is climate. We are going to change over, somewhere between 50 and 100 trillion dollars of infrastructure worldwide into new generations of infrastructure that's zero carbon. And we have to do it. We're going to be forced to do it. We have to do it. It's the right thing to do. And that's in and of itself is going to be the biggest companies in the world. And so sort of the Tesla and other battery EV companies have shown a path forward. And we've seen a lot of capital come into this space. I hang around a whole lot of venture capitalists that lost a lot of money in Clean Tech 1.0 in 2008. And this feels very different. And it's increasing, and the ability to get capital for things that are hardware intensive, that are a longer duration, the ability to try to parse what is a good thing to put money into, those are all getting better. And that's I think a very good sign for fusion, but it's a good sign overall for the energy ecosystem, and it's particularly a good sign in the United States, where most of that capital flows and where you have the entrepreneurial sort of spirit and centers in the coasts and growingly in the middle to take advantage of those opportunities.
Steve, any comment on the role of private capital?
I'm a little out of my depth with private capital, Paul, but what I will say is that we receive a lot of inquiries because people are very interested in fusion right now. I'm interested, Bob, that you say it's hard to raise money, because I think you've done very well, and so have some of the other companies in exciting a group of investors to really push things forward.
So I'd like to ask a question about the role of traditional global energy producers. There's a question here about that. There was a panel that the Stellar Foundation in Princeton did recently with Ralph Izzo, the CEO of PSE&G, which is one of the big utilities with a big fission fleet, and a graduate of and did research at Princeton Plasma here a couple of months ago. Obviously, there's if you kind of maybe focus on the electricity aspects rather than transportation or space applications or so on, just more of the terrestrial, straight up the middle, potential electricity application. How do you all see those existing large energy players participating, being partners in what needs to happen in this fusion sector?
Yeah, so I have CFS. Those are our customers, right? That's we have to be a customer-centric organization. Our goal is to sell power plants to people that want to use them to make money. And when you look at the types of customers that are out there, it's really approaching the Wild West. It's not where we were 20, 30 years ago. Deregulation in the industry in the United States and also globally, has led to all sorts of different types of entities that buy and sell and own power plants. Whether that's the traditionally regulated large southeastern utilities like Southern, who can build something like Vogtle, or whether that's like a NextEra. To think that the biggest, fastest growing energy source, was a tiny power producer in Florida that's now worth more than Exxon, or whether that's the large oil and gas companies who are looking at their future and saying, well, hey, we know how to find, generate, and move energy. We don't care if it's a pipe or a wire. And so it's, or whether it's the tech companies who are energy consumers in their own right at a level of governments. And so all of that is, I think, a very exciting time where the policies are changing, the players are changing, and the different ways to find a match between the product and the customer is widening up in big ways. And from a CFS standpoint, we have Equinor and Eni, the Norwegian and Italian large super major oil companies, as big investors, and that was board level decisions for those companies as they plotted what the future of energy was and where fusion could fit and how disruptive fusion was. And so they've actually built fusion divisions inside those companies, particularly Eni, to try to take advantage of the shifts. And so I think it's a very a lot of players, a lot of movement, and it's not simply the if you build it, the utility will buy it model anymore.
There's also sort of interesting shifts in the energy world, and if we start to have dedicated plants to produce liquid fuels, for instance, we have dedicated plants or maybe several plants together because we have sort of a massive liquid fuel factory. Or we have concentrations of steel producers, aluminium producers. Fusion would serve those markets in very particular kind of ways because of being a firm energy source, being one that can be very close to, because of its intrinsic safety features. It can be close to people. It can be within a community or right next to a factory, that kind of thing. I'm very interested, I think, in looking at the ways that as you start to produce an energy source like this, it's not just, replace a power station here and replace a power station here, but the energy system in the world is going to look very different in the future when, for instance, maybe we have to produce liquid fuels for airplanes.
So there's a question here about effectively around centers of excellence and NASA references, and do we need something for fusion? So, question in here about NASA has still to this day has JPL, right? It still has obviously Cape Canaveral has turned very interesting from 100% government site to really a mixed use case, public-private facility. It's extremely dynamic right now as a result of that real estate and those capabilities. Do you think that fusion needs, something like that in which there's some innovation hub that, notwithstanding, once again, using the NASA reference, there's a lot of different data points around the country and Blue Origin and SpaceX and elsewhere, but still there's these kind of still concentrated efforts for R&D at JPL and support and so on at Huntsville and so on. Do you see any, as you think farther out, let's say Bob hits in 4 years, 10 times net out, like his paper says, is there still a need for certain hubs of innovation that maybe policy should think about supporting, like those examples I just gave? Steve, maybe I'll throw that to you.
Yeah, well, that's very interesting, because if you look at the examples you're giving, they're somewhat different, right? JPL is one of the world's great centers of understanding aerodynamics and space flight and things like that. But it's not the place you actually launch the thing. And I think this is going to be true in fusion too. And I'm particularly aware of it because I'm at Princeton. Princeton's is not going to be the place that we produce a pilot plant. It's just not an appropriate place to have a pilot plant. And pilot plants will probably be on some big energy site somewhere in order to take advantage of different kinds of facilities that are there. But Princeton will be going into the future thinking about fusion, because the first generation of fusion won't be the end of the story. I mean, airplanes don't look like the Wright brothers flyer. And there'll be many generations of change as we go through this, and keeping the capability to think about this problem and start to innovate towards smaller, cheaper, faster fusion reactors. There should be a national center for that, and I know where that should be. I'm sitting in it right now.
I didn't quite set you up, but it was close.
Yeah, it was.
Bob, what do you think? I mean, as a private entity, right? Your kind of reference to SpaceX versus Canaveral or JPL.
Yeah. I think Steve's got the essence of it, which is, at the end of the day, for fusion to make the difference that we all hope it does, we have to manufacture it, and we have to distribute it around the world, and we have to build a lot of them. We have to build them in communities that are accepting of them, and communities that is equitably distributed. We have to do a lot of different things, and a lot of those things, are where the rubber meets the road between the market and the product and that mode of delivery. And that's really where the private companies they can they should excel there. That's where their value is going to be largely created. But that's not the whole story, because there's beyond that, there's also the things that are going to support the technology, the continued technology development. How do we get new materials? How do we make the simulations better so we can be more and more predictive, so we can be more and more optimized? How do we take ideas that are not ready to have private capital put into them, but are intriguing new concepts that could produce simpler or better or fusion systems that are more adept at filling a need for, liquid fuels, as you said? Those are all things that need to happen. And many of those things, happen in a clustering effect, where if you have a place where people mix and different disciplines come together that has tools and capabilities, those types of centers can really bring a whole industry forward. And I think if you're in any given industry, you can identify a center of excellence that either grew organically or had some help being planned to do those functions. The key thing is understanding that it's not the job of the federal government to design a commercial product, but it is the job of the federal government to provide the tools and pieces that are going to lift the science and lift the understanding up so that other people can build on top of that and to continue to drive that innovation engine forward. And really making sure that we've got centers and roles and responsibilities that really capture the handoff, and so they're not throwing it over the fence, but we're instead passing a baton.
So I have a question here from a colleague at Columbia, Cheryl LaFleur, who is former chair of FERC, obviously a national expert on the energy markets. And she had a question about the acceptance by the general public around fusion versus, the public doesn't in general have a great understanding of the differences between fission and fusion. And obviously FERC and state regulators and others have roles to play in citing and public interest on any topic of citing. Obviously is very important for people like when she was chair or any of the other entities. How do you think that's that awareness campaign should be accelerated or executed upon?
So I thought that first get data, where people are, how they're thinking about it. And I thought the UK did a great job of this in their regulatory survey. They surveyed a lot of people and came away with people that knew about fusion were generally very pro, and people that didn't know about fusion were importantly neutral. Which means that we're starting from a place right now where we have a chance to get this right. But that means we have to put the work in to do it, and we have to put the work in by showing that what fusion can bring, what are the benefits, but also being transparent about what the potential consequences or downsides are. And that's an approach of social acceptance that has worked for other advanced technologies. And there's things that we, for instance, so we're building our next machine, Spark, outside Boston, and we were very particular in where we were going to build that and what community we wanted to be in and how we'd approach that community, because we want to set a good example. And I think actually Princeton did a great job of this in the 80s, late 70s, when they built the large machine there. But it really comes down to boots on the ground, explaining to people, particularly the people that are most affected by it, what it can do for them. And what it can't do for them. And right now we don't actually even have a part of that in, say, the policy circle. Like where is the policy center for how public acceptance will impact fusion? That will be as important as the computational plasma physics. And those are areas that are gaps, clearly.
One of the things that I've been thinking a lot about, because we're starting a process which actually you, Paul, started when you were undersecretary, which was to talk to the NRC about fusion and how we would see regulating it in the United States. And one of the things that's important for the researchers here is what would help us get a system that has a lot of public acceptance and very low regulatory framework to keep it. Because fusion does have neutrons. At least DT fusion has neutrons, and they can activate things, but you can choose, unlike in fission, you can actually choose the materials you're using so that activation is very short-lived and it's not a problem at all. But how much is it worth it to you, and from a regulatory point of view, and how do you want to go forward? So I think we're in an interesting discussion period at the moment as to how do you optimize that? Do we not care about this, but we really care about that? And part of this is public acceptance, and I'm not really a very expert on that, but I think the points Bob make are very important. We're in a good place to get started. And as we get started, I want to make sure that fusion has the possibility of being sited, right next door to a major population center, because one of the great things about fusion is you don't need to use very much land, and that it's a firm energy source, and therefore you would like not to have to sort of put it away from people. You'd like to have it right there, and that just requires making sure that the designs respect that.
So there's a question here from Sandeep Sen about about, are there any utilities, effectively customers at the end of the day for electricity? Are you seeing any engagement either at the lab or at CFS who are wanting to engage yet? Or maybe not. It may be too early for them, and maybe there should be venues to try to figure out how to engage with them. So, Bob, what's the status right now of those what I call logical customers, so to speak, interest?
Yeah, the increasing interest, increasing engagement. We haven't yet seen anyone write fusion into a long range resource plan, but I don't think it'll be that long until we do see that. Certainly, they are starting to take a look at the frameworks around how to think about it. So places like EPRI and the Edison Institute, who are traditional aggregators of the utilities, they've started fusion discussions and groups. And then additionally, policy, we're starting to see like the Edison Institute have fusion policy as part of their platform of what the utilities want to see. And so you're seeing increasing engagement. The venture arms of the utilities have made some fusion investments, which is a way to get exposure to the overall field. I think that's positive. And then, at the individual utility level, where we see, incoming weekly and briefings on where things are going. And I think that's, they're certainly going and asking lots of other people about how to think about this. What's the timeline? What's the markers on the path? And, fortunately, energy planners have long-term plans. So they're able to handle the uncertainties and ambiguities of a long-range plan. And there's some of the funner conversations that I've had.
I think it's very significant that Ralph Izzo, the chief executive of PSNG, is serving on FESAC, which is the Fusion Energy Science Advisory Committee of the Department of Energy. I think Ralph, his time is very valuable, and I think his input to that panel is extraordinarily valuable because it's about keeping eggheads like me understanding what it is that we really should be aiming for at this time. If I started out by saying we're in the end game of fusion, if we're really in the end game of fusion, we don't want to produce something that the market doesn't want.
So I think we have a few people here who are leaders of academic departments at universities and one, I think it was effectively a question: if a university doesn't have a large endowment, a current large existing program for fusion like Princeton and MIT have, but they're interested in participating both in research and in producing graduates along the lines, Bob, you were talking about earlier. What sort of recommendations would you give science or engineering departments who want to participate in some of these sort of things?
I'll give that, Steve, you should definitely take that one. I've never hired a faculty.
It's a very interesting question because as modern research builds out in these areas, obviously the experiments will tend to be in certain centers. But modern research is like that. And a faculty member can have a big program on one of our machines at Princeton or on Spark in Massachusetts, either by visiting or these days, people sit at home on their computer or in their academic department pulling down data from machines because everything is online now. And we broadcast our operations, and there are remote control rooms for machines all around the world that come from these places. This is allowing smaller academic units to be participating in big science in ways that they never could before. And I think it's a tremendous help. And we at Princeton, and I'm sure MIT, would welcome faculty members from other places to be part of our teams, but in an extended part of our team. And the Department of Energy actually funds that, and will provide funding to those academics in their departments to work on machines at other places and to be involved in those things. And similarly, we're developing big codes, big simulation codes to simulate the plasmas of the future. And those simulation codes are built by people all over the world. And they participate, especially since the pandemic. You know, the pandemic has not all been bad. We've learned to collaborate in ways that we never collaborated before. It's no substitute for, you know, actually being in the same room. But in addition to that, it's going to be a tremendous help. So, you know, so open up a faculty position. Contact me or Bob about some of the leading, you know, early career people in these areas, and you know, and so you can get a good short list of very, very smart people. We're getting, you know, really top-notch undergraduates applying right now to do fusion.
Yeah, I think this this broadening academic involvement beyond no disrespect to the greatnesses of MIT and Princeton and elsewhere, but there's a lot of political interest in broadening, and I think beyond political, just kind of practical and economic, you know, interest and broadening innovation and R&D and funding, you know, more broadly across the U.S. So I think this fusion question was consistent with other similar questions about the broader topic. And I'll give one last question here to former Deputy Undersecretary Cubbage to ask about supply chain and critical materials. You're both building and constructing and having to have to deal with topics. Obviously, it's quite topical nowadays to talk about critical materials and supply chains and fragility of those. We've seen that quite well here recently, more broadly. But obviously, things like HTS materials, lithium that could lead to tritium. I mean, these things are all, you know, topical into broader technologies. But how do you see that as you're building and you know, looking at supplies for both your facilities?
Yeah. So, you know, for us, we always start from first principles. So like what is needed, what are the atoms, where do they come from, and how many of them are mined right now? And you know, we have to have an answer for what that looks like at full scale. You know, at a fusion assuming that we are successful in a fusion industry is built off of our technology. And the big advantage of fusion is that those answers, you know, are different than the short-term answers. The short-term answers might be, you know, who exactly can make this one thing today that's new. The long-term answers all, for the most part, point to fusion should be universally achievable. It should be something that doesn't have critical materials. There are ways to deliver these machines so that basically what's under your feet anywhere in the world is what you need to build fusion machines or within your water. And so even things that seem, you know, sort of like esoteric, like, oh, you know, for HTS, well, the HTS actually, the amount of weird stuff in it is like a dopant. And so even at full scale, it doesn't really impact the market that exists today. And that's a big deal for fusion. It's like, you know, basically moves fusion into this realm where it's not really about a resource, whether that's a critical material or the oil or coal under us. It's just something that's like, can you build this machine? And can you operate this machine? Can you optimize this machine? And so there are definitely shorter term challenges. Like now there's an acute challenge of like, you know, we can't buy the right steel or get stuck on boats, which is just something that shows you how interconnected the world is. And when it doesn't quite work right, it really throws wrenches. But long term, you know, the fact that the numbers all work out for a very large fusion industry is really heartening.
There are a few materials that it would be nice to have more of. If you don't necessarily have to use them. Beryllium, for instance, largely comes out, I think, of Central Asia, the beryllium supply in the world. And that would be nice to have. We've been building, because this is a very interesting idea, how to make stellarators using permanent magnets and some superconducting magnets. And we've been building one of the world's largest permanent magnets with a great deal of structure in it with a small company out of Boston, Massachusetts. And suddenly the price of, you know, neodymium has doubled in that time. And that is a pain for us. But I don't think it's a long-term issue, because I think if we really need a lot of neodymium, we'll be able to get it. in the future. And there's a possibility, for instance, of making very high field permanent magnets just out of nitrogen and iron. That would be lovely. So I'm confident we're not going to have a roadblock in this respect, but it would be nice to find some more beryllium.
Okay, well, thank you very much to the both of you and everyone. Very large number of people who were here live with us, watching the two of you. Obviously, I think this is incredibly helpful for the community, but also people who are not normally part of the fusion community to learn more about what's going on. I think your thoughts around policy for those people who are participating. Thank you for both of you for the suggestions. As we mentioned, the full video recording of this event will be available on the Center on Global Energy Policy website in a few days. Our next event is Exploring an Uncertain Energy Future. Equinor's Energy Perspective 2021 will be held on Wednesday, October 20th at noon Eastern Time in the U.S. And a full calendar of upcoming events, please visit the Columbia Global Energy for Center Energy Policy online. And I think the link is up for you all. Thank you again for both of you participating and just helping move the dialogue forward. And thanks to everyone who